Okay, in this video we're looking at a review of congruent triangles. We're looking at applying that in the sense of a proof, and then we're also looking at an introduction to some circle geometry. So starting off with our congruent triangles, there's a couple of abbreviations that we use to describe our 4 different cases of congruent triangles. So in the first case, 3 sides of one triangle are congruent to the 3 sides of the other triangle. So that is side, 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 which we refer to as SSS. When 2 sides and the included angle of one triangle are congruent to the other, then that is side, angle, side. And the order of that is important because the angle does need to be between the 2 congruent sides. If we have 2 angles and then a side, if we have 2 angles, it means we have the 3rd angle because all angles in a triangle have to add up to 180 degrees. So that one side is enough to give us congruence. So this is angle, angle, side. And then if we have the hypotenuse of a right angle triangle, and we have one of the sides, as well as the fact that it is right angle, that is also enough. So this is our right hypotenuse side. So if we wanted to demonstrate that the diagonals of a rectangle are congruent, we would have to use some of these ideas. So first of all, what are we going to do? We need to draw our rectangle. What are we trying to prove? Well, if there's our rectangle, let's call it A, B, C, D. And essentially, we want to show that the diagonal that goes from A to C is congruent to the diagonal that goes from D to B. So to do that, we're going to break this rectangle down into the triangles that we've just created. So we've got 2 triangles. We've got the triangle ACD and the triangle BCD. So we can see those 2 triangles that we've discovered. And all we're trying to do here is show that the hypotenuses of those 2 triangles are the same. So to do that, first of all, we know that AD is going to be congruent to BC. That is to say, this line here, AD, is the same as this line here, BC, because it is a rectangle. So when you're in a rectangle, 2 of your sides, you've got 2 pairs of equal sides, so that's the shorter of the 2, and then we'd also have AB is congruent to DC for the same reason, because it's a rectangle. The last bit of information we need is an angle, right? So the angle between these 2 lines, so for instance, if we were to take DC and BC, well, we know that that's going to be 90 degrees down here, and it's also going to be 90 degrees up here. So we have that angle ADC is equal to angle ABC because they're both 90 degrees. Therefore, we have that the 2 triangles ACD and BCD have to be congruent. So if they're congruent by side, angle, side, we have that their hypotenuses are also congruent. So we get that AC is congruent to BD, therefore the diagonals are congruent. So what we've seen there is by breaking down quadrilaterals into triangles, we can often apply our congruent triangle theorems to also show that the sides, or in this case the main diagonals, are also congruent. Okay, so moving on to circle properties 1. So this is angles in a circle as well as chords. So some definitions surrounding chords. The distance around the circle. So if you were to trace around the circle, the distance that you've gone is of course the circumference, but we also use the circumference to describe the line that's drawing that length as well. We also have that the center of the circle is the middle point, and it's equidistant from all points on the circumference, and we often refer to it as point O, meaning like the origin or the center point. A chord is an interval joining 2 points on the circle. So we have a couple chords here. We've got A to D, we've got A to G, and we also have G to D. So even though it goes through the center, it's still a chord because it's taking us from a point on the circumference to another point on the circumference. So examples of these are AG, AD, and GD. We have a special name for a chord that passes through the center. That is, of course, the diameter. And the name for any straight line joining a point on the circumference to the center is, of course, a radius. We then also have some definitions. Before we go to that, let's look at what radii we have on this circle in the top right. So we can see GO, DO, and FO are all examples of radii. Radii being the plural of radius. So moving on to some angle definitions. So the part of a circle defined by 3 points, for instance, here A, B, and D. So A, B, and D, we refer to as an arc. So ARC, and to notate an arc, over the 3 letters that define our arc, we draw a sort of semicircle or an arc above it. A minor arc is smaller than a semicircle, a major arc is larger than a semicircle. The angle AGD, so if we're looking at AGD here, is called an angle at the circumference subtended by the arc ABD. So subtended, fancy word that sort of says, if this is our arc here, ABD, if I take one point at one end of the arc and one point at the other, and then I connect them up at another part, that arc subtends to that point. So this angle here is subtended by the arc ABD because sort of the endpoints share that arc over there. It's sometimes also described as standing on the chord AD. So if instead of looking at the arc ABD, if we just looked at this chord here, AD, we can say that this angle is standing on that chord. The angle at the center is the angle made by 2 radii intersecting at the center of the circle. So, for example, here we have the angle FOD, so angle FOD, that angle there, as well as the angle GOF in this case, or FOG. Angle FOG and angle FOD. Right, and then lastly, the angle in a semicircle, in our case here, is the angle GAD. And it's called an angle in a semicircle because the point GD, the chord GD is a diameter. It goes through the center. So that chord GD is cutting this into a semicircle, so an angle in the semicircle is GAD. Right, we then have some useful theorems for angles in a circle. So theorem 1, the angle at the center of the circle is twice the angle at the circumference subtended by the same arc. So we have an angle here, x. The angle at the center subtended by the same arc is going to be 2x. It's going to be twice. And when working in our solutions, we don't like writing out sort of this theorem every single time. So instead, we just draw a symbol that represents that concept. Okay, the second theorem. Angles at the circumference subtended by the same arc are congruent. So if the magnitude of the angle at the circumference is x degrees, then the magnitude of any angle at the circumference subtended on the same arc is x0. So no matter where I put these 2 lines out to, wherever they meet is always going to be x degrees. So again, we notate that as sort of an hourglass looking shape. And we're basically just drawing 2 angles subtended by the same arc. The theorem 3, the angle in a semicircle is always a right angle. So if one of your lines is the diameter, the other 2 lines will meet at a 90-degree angle. For this one, we just draw a semicircle containing a right angle point. Okay, so let's put some of this into practice. Determine the values of A, B, and C in the circle shown. Well, from the get-go, we can see this angle B is subtended by the same arc, AED, as angle ABD. So angle ABD is equal to angle ACD, which means B is equal to 28 degrees. Now, to communicate how that's the case, I need to draw my symbol. So in this case, it's going to be two angles subtended by the same arc. Okay, now looking at the angle at AOD, so this part A, or this variable A, we can see that the angle ABD is subtended by the same arc to the center. So we've got that this angle is going to be twice as big as this angle. So angle AOD is equal to 2 times angle ABD. And why is that the case? Well, it's this symbol here showing us that the angle in the center is double. So we get A is equal to 2 times 28 degrees, which is equal to 56 degrees. Now notice, I could have said the same thing here about ACD, but I chose not to because if I made a mistake up here with my value of B, I know in this case it's just copying it 1 for 1. But if I made any mistake here and then I used that angle that I only just calculated, I might end up having a follow-through error here. So wherever I can, I'm always going to try and use information that's given to me in the question as opposed to information that I have discovered from the question. Because if I somehow misread that it's 26 and then I made this 52, you can see that flow-on effect happening. Okay, and the last one we have is angle CAD. So to find that, we have the angle B. We want to find this angle. Notice how the lines ACD make a triangle, right? And not only that, it's a triangle with a diameter as one of its lines. So that means this angle here has to be 90 degrees. Well, if I know 2 of the angles, then I can also find the third. So first of all, we know that angle CDA is equal to 90 degrees because it is in a semicircle. Therefore, we know that B plus C is equal to 90 degrees because angles in a triangle have to add up to 180 degrees. So we can solve for C to be 90, take 28, which is equal to 62 degrees. All right. So that was using all these theorems to find the values of pronumerals, but what if we're asked to prove a theorem? So theorem 1, which just as a reminder is the angle at the center of a circle is twice the angle at the circumference subtended on the same arc. So let's first of all draw what this looks like. There's our circle. There is our center. We have some point on the circumference, and the arc subtends to the center, and we're trying to show that this angle here is twice that angle up there. So to do that, what we are going to do is create diameter from A to D that divides the quadrilateral in half. All right, so this sort of funky looking shape here is a quadrilateral. It's got 4 sides. We want to create a diameter that divides that in half. It might not be exactly in half, but in our case, it is. So remember, this point doesn't just have to be on the same diameter. It could be over here, at which point we'd divide it through like this. What this does is it splits this angle up here into 2 components. So let's call them X and Y. To make this a little bit clearer, and as we start using our triangle notation, we want labels for all these vertices. So let's call this A, B, C, O, and D. So that gives us our diameter A to D. So we've divided this quadrilateral. We can see that this line here, CO, and this line here, BO, must be the same because they are radiuses, or radii, sorry. And we can see that A to O is also the same because it is also a radii. So what this gives us is two isosceles triangles. So AOB and AOC are both isosceles. So triangle AOC and triangle AOB are both isosceles. What that means is the angles CAO is equal to the angle ACO, which means that this angle down here is also X, and similarly we have something for Y. So we have that the angle OAB is equal to the angle ABO. Right, so now we know that both of these are equal to each other. So what we get is this angle here, which is what we're trying to prove, right? We're trying to prove that that is double this angle. Well, it's going to be 360. Take this angle, take this angle. So what we get here is that 360 minus, well, what is this angle here? That's going to be 180 minus 2x, right? 180 minus 2x. And then this angle here is going to be 180 minus 2y, because angles in a triangle add to 180. So we're also subtracting 180 minus 2y. And that is going to give us the angle COB. Right, so with that angle, we can see that that angle is equal to 360 take 180, take 180, which is 0. And we're also going to get minus negative 2x is positive 2x, and minus negative 2y is positive 2y. Well, that is just double x plus y, which is equal to 2 times the angle CAB, which is what we were trying to prove. So we can see the angle at the center is twice the angle at the circumference subtended by the arc CDB. Okay, some further theorems that are useful for chords. So theorem 4 states, if a line from the center bisects a chord, so splits it perfectly in half, it is perpendicular to the chord. The converse is also true. If a line from the center is perpendicular to a chord, it bisects the chord. The symbol we give for that is a circle with a line that comes from the center into a chord, and then 2 dashes showing that the 2 halves of the chord are equal. I'm just going to draw that a little bit more clearly. There we go. Okay, theorem 5. If chords are congruent, then they are equidistant from the center of the circle. So if the length of this chord is equal to the length of that chord, then the distance away from the center has to be the same. So that's why we've got this little tick here, because these two are equal. So the symbol for that is just 2 chords with 2 lines showing that they're equidistant. Theorem 6, if 2 chords intersect inside a circle, so if they intersect at this point E, the product of the lengths of the segment for both chords is the same. So that is to say, BE times DE, so the length of this times the length of this, is going to be the same as the product of the other 2. Symbol we give for this is just a circle with 2 intersecting lines in the middle. Okay, theorem 7 looks to be the most complex, right? We've got many lines here, and what we're saying here is congruent chords subtend equal angles at the center. So if AB is congruent to BC, then the angle AOB is equal to the angle BOC. And the symbol we get for that is really just a recreation of what's over here. So we've got our dot in the center, we've got two triangles coming out from the same points, we have two chords either side, and then dotted lines going to the center. So let's put this into practice. Example 30. If AB equals BC is equal to 15, find the angle OBC and find the distance of EC. So let's first label what we're told. So these two distances are 15 and they're equal to each other. So what that means is OB bisects the chord AC. So if OB bisects AC, then the angle OBC has to equal 90 degrees. And the symbol we give for that is a chord bisected. That's part A. Part B, we want to find the distance of this chord here. Well, these chords are equidistant to each other. So as OB and OD are the same distance, we know that EC is going to be congruent to AC, and the symbol we draw for that is just our two equidistant chords. So if that's true, we then know that EC is equal to 15 plus 15, which is just equal to 30. Okay, our last example for this video is looking at proving Theorem 4. If a line from the center bisects a chord, it is perpendicular to the chord. So we have our circle, we have our center, we have our chord, and we want it to bisect it. So let's label this, let's call it O, A, and B, and we want to show that the angle from O to the midpoint to A is equal to 90 degrees. This is what we're wanting to prove. Right, so let's label this midpoint. We know it's the midpoint because it's bisecting it, and that's what we're trying to find. So what we want to apply here is congruent triangle theorem. So instead of having three lines, let's turn this into two triangles. Okay, and the reason why that's helpful for us is we can see O to A is equal to O to B, right? O to A is a radius, O to B is a radius. So we know that from this we have OA is congruent to OB, OM is shared, and we have that AM is congruent to MB. So what does this all add up to? Well, we know that the two triangles are congruent. Let's actually write this out properly. So we get that triangle OMA is congruent to triangle OMB by side, side, side. All right, so we have three sides showing that they're congruent. So if they're congruent, then the angle OMA has to be equal to the angle OMB. But they also have to add up to 180 degrees because they are supplementary to each other. So that's our supplementary rule there. So if they're equal to each other, we can substitute this into there. We get that 2 times angle OMA is equal to 180 degrees, which means our angle OMA is equal to 90 degrees. So we can see there that yes, indeed, if a line from the center bisects a chord, it has to be perpendicular to the chord. And that's all for this video. Thank you for watching.